Hello, my name is Kirti. In this video, I am going to talk about Arrhenius equation. This topic is important for both CSIR-NET and GATE exam. So we will do it the way we usually do. That is, in this video, I'll cover the theory portion of the concept. We will see what is Arrhenius equation, what does it explain, and at the end, we will also see different forms of this equation. And in the next video, we will solve few problems related to this topic. Okay, so let's begin. So we know that Arrhenius equation gives us a relationship between rate constant, activation energy and temperature of a reaction. So this equation is given as K is equal to A e power minus EA over RT. So here K is the rate constant. So K represents rate constant. A is the pre-exponential factor. Pre-exponential factor. EA is the activation energy. EA is the activation energy. Activation energy. R is universal gas constant. UGC. Okay. This means universal gas constant. And T is temperature. So T is temperature. So I hope you know what is rate constant. Okay, I'll explain it here what is rate constant. Suppose consider this reaction A plus B giving rise to product B. And suppose the order with respect to A is N and order with respect to B is N. We know that rate of any reaction is proportional to the concentration of the reactants to the power of their order. So rate is proportional to the concentration of A to the power M and concentration of B to the power N. Now when I remove this proportionality symbol, I can put a constant here. So this constant is the rate constant. Okay. So how can we write this? I can write K as rate divided by K is rate divided by A to the power M and B to the power N. So when will this rate become equal to rate constant? When concentration of A and B are taken as unity. Okay. So when A is equal to 1 and B is equal to 1, R will be equal to K. So can I define rate constant as rate of the reaction per unit concentration of reactants? Yes, right? So this is the definition for rate constant, that is, rate constant is the rate of reaction per unit concentration of the reactants. So now you know what is rate constant. Okay, there is one more condition when this R becomes equal to K, that is when M and N are equal to 0. Okay, so A power 0 becomes 1, B power 0 becomes 1, then rate will be equal to rate constant. But do not consider this equation to define rate constant. Okay. So rate constant is defined as rate of the reaction per unit concentration of the reactants. Okay, now you know this. I'll explain you what is pre-exponential factor and activation energy. I hope you know what is our universal gas constant, and if you do not know, I have already made a video on significance of universal gas constant. So I'll give the link in the description. If you want to know more about R, you can look at that video. Okay, and T is the temperature. Here we need to know one more important thing, that is this equation, this Arrhenius equation is an empirical equation. Okay, this is empirical equation. So what do I mean by empirical equation? So empirical equations are those equations which do not have any theoretical background. So this is given on the basis of experimental observations. So if any experimental data, if you have some experimental data and if it repeatedly fits to a particular equation, then that equation is considered. Okay, such equations are called empirical equations, which are given based on the experimental data. So these equations do not have theoretical background, and since they do not have any theoretical background, they will not have derivation, right? So there will be no derivation of Arrhenius equation. So you need to remember this equation. You need to know it by heart, okay, since there is no derivation. So then if there is no derivation, how can we justify this equation? So this equation can be best justified or explained on the basis of this theory called collision theory. So in this video, we will superficially see what is collision theory so that we understand how this theory explains this equation, okay. So now we'll learn what is collision theory. So collision theory predicts the rate of gaseous reactions. Let me ask you one important thing. For any reaction to happen, what is the primary criterion? The primary criterion is that the old bonds in the molecule should break and the molecule should form new bonds, right? So this happens only when two molecules collide with each other. So the requirement for any reaction to happen according to collision theory is that the molecules should collide with each other. So according to collision theory, rate of reaction is proportional to the number of collisions. So rate is proportional to number of collisions happening per second. Okay, number of collisions per second. So this is also called collision frequency. So this number of collisions per second is also called collision frequency, and it is given by alphabet Z. Okay, it is represented by Z. So more the number of collisions, faster will be the reaction rate. Okay. Okay, now there arises one more important question, and that is, do all the collisions lead to the formation of product? Okay, let me explain you this way. Suppose this is our reaction vessel and we have reactant molecules, and all these molecules collide with each other since they are in random motion, right? There is probability that one molecule collides at least with one other molecule, okay? So do all these collisions lead to the formation of product? That is the main question. No, because the answer is no. Because if all the collisions lead to the formation of product, then rate of these reactions would be much faster. But experimentally, it is found that rate of gaseous reactions is not as fast as expected. Okay. Therefore, they came to a conclusion that all the collisions do not lead to the formation of product. There are certain collisions called effective collisions or fruitful collisions that will give you products. So rate will be proportional to effective collisions or fruitful collisions. So we'll in a while see what are these effective collisions, okay? So till here we saw that rate is proportional to the number of collisions per second, that is collision frequency. But all the collisions do not lead to the formation of product. There are certain collisions which are called effective collisions that will give you the product. So now let us see what are effective collisions. Now these effective collisions can be explained on the basis of energy profile diagram. So I will draw it here. So energy profile diagram is the graph between energy of reactants and any reaction coordinate. So this reaction coordinate can be time, concentration of products or concentration of reactants. So for now I will take reaction coordinate as time. So this diagram looks something like this. Okay, this graph looks something like this. So here you have reactants and on this side you have products. So now from this diagram we see that reactants should cross this energy barrier to become products. Suppose this energy is some 100 joules, okay. So the reactants should have 100 joules of energy while colliding to form products, and this minimum energy is called threshold energy. Okay, so this is threshold energy. So if there are 100 molecules or 100 reactant molecules, and out of them the molecules that have this threshold energy while collision only will give two products. All the 100 molecules will not give you product. Okay, so there will be, say, some X molecules out of 100 which will give you product. So here we see that the reactant molecules already have some energy. That energy is because of their kinetic energy or internal energy, right? So reactants already have certain amount of energy, and they now need this much amount of energy to cross this energy barrier. Suppose this is, say, some 40 joules. Okay. Now this reactant molecules need to acquire additional energy of 60 joules to cross this energy barrier, right? So this energy, this additional energy that reactant molecules need to acquire to cross the energy barrier is called activation energy. So this is EA. So EA is given by threshold energy minus energy of reactants. So activation energy is equal to threshold energy minus reactant energy. Okay, or energy of reactants. So this is activation energy. Now here we see that rate of reaction is proportional to the effective collisions, and only the fraction of molecules which have this threshold energy will give you effective collisions, which leads to the formation of product. So this fraction of molecules which have this threshold energy is given by Boltzmann distribution. So according to Boltzmann distribution, at temperature T, E power minus EA over RT molecules will have this threshold energy. Okay, we are not going into the derivation of this Boltzmann distribution. Okay, it is the subject of statistical thermodynamics. So we'll just use this formula. So what does this say? What does this distribution give you? This gives you the fraction of molecules that have this threshold energy to cross this activation energy barrier. Okay. So this fraction depends both on the activation energy and temperature. Okay. So rate is proportional to effective collisions, and effective collisions are given by this factor E power minus EA over RT according to Boltzmann distribution. So now if the molecules have, suppose if the molecules are colliding, and if they are colliding with this this much threshold energy, okay, so do they lead to the formation of product? I'll come again. So we have two molecules, two reactant molecules, they are colliding with each other. So that is the primary requirement for this collision theory. They are colliding with each other, and they are also colliding with this threshold energy. I mean, while collision, they have this much amount of energy. Then do those molecules necessarily give you products? That is my question. I can explain it with this example. Suppose consider this reaction, hydrogen iodide decomposing into hydrogen and iodine. Okay. Suppose this is one hydrogen iodide molecule. This small circle represents hydrogen and big circle represents iodine. We know that hydrogen is much smaller in size when compared to iodine. So this is one hydrogen iodide molecule. It is colliding with other hydrogen iodide molecule which is oriented in this way. So this molecule will have, say, 100 joules. Each molecule has 100 joules of energy. So they satisfy this condition of threshold energy, and they are also colliding with each other. Now will these molecules give you this hydrogen and iodine molecule? Suppose if they are colliding in this direction, we see that this old bond will break, this bond will break, this bond will break, and there will be a bond formation between these two and these two atoms. Okay. So what will we get? We will again get back hydrogen iodide, right? So this is Hi, this is also Hi. So there is no reaction happening, right? These molecules, they are colliding and they also have this threshold energy while collision. Even then, these molecules are not giving us the products because their orientation is not proper while collision. So rate of reaction not only depends on effective collisions but also depends upon the orientation of the molecules during collision. Suppose if these molecules collide or orient in this way while collision. So they are colliding with each other and their orientation is like this. Now these old bonds will break and new bonds form between these two and these two atoms. So now what we have is, so this is hydrogen, this is iodine. So proper orientation will give us our products. Okay. So rate of the reaction also depends upon or proportional to this factor called orientation factor. So the reactant molecules need to be properly oriented during collision. So from here we see that rate of reaction is proportional to the collision frequency, that is number of collisions. It is proportional to the effective collisions, that is the number of collisions that have this threshold energy or number of molecules that have this threshold energy while colliding, and it is proportional to the orientation factor, and this orientation factor is represented by the alphabet P. Okay, so this is given by P. So when we combine all these three conditions, okay, give me a second. So when we combine all these three conditions, we see that rate of reaction is proportional to Z, that is total number of collisions, and F, which gives you the fraction of molecules having threshold energy or effective collisions, and P, which is called orientation factor. So now we know that, suppose if I consider the proportionality as constant as 1, I can put equal here. So we know F is e power minus Ea over Rd. So it will be rate is equal to Z into P into e power minus Ea over Rd. So when I compare this with Arrhenius equation, that is K is equal to A e power minus Ea over Rd, we see that these two equations are very similar. Okay, this Z into P is a constant and here we have A as a constant. So from this we can say that Arrhenius, what is this? P exponential factor is Z into P, and this term also match. So this is how collision theory explains this Arrhenius equation. And here rate can be equivalent to rate constant when concentrations of the reactants is considered as unity. So there is no problem with this, right? And so we see that collision theory best explains this Arrhenius equation. So from these two equations, P exponential factor is equal to collision frequency into orientation factor. Now later you will see that this A also depends on temperature. A is not a constant but it depends on temperature. Okay, now we know what is Arrhenius equation and how collision theory explains this equation. Now we will see how this temperature and activation energy will affect rate constant or rate of a reaction. That means what happens to the rate when I increase or decrease the temperature, or when I increase or decrease the activation energy. Okay. So the equation is K is equal to A into e power minus Ea over Rd. Now let us see what happens when I increase the temperature. Suppose, okay, before that we can write this as A into 1 over e power plus Ea by Rd. Okay, we know that A power minus n will be equal to 1 by A power n, right? So this is similar. E power minus Ea over Rd is equal to 1 over e power Ea over Rd. So now when I increase the temperature, what will happen? This term Ea over Rd will decrease because you have temperature in the denominator here. So when this denominator increases, this whole term will decrease. Now what happens to this e power Ea over RT? So this term is decreasing, then e power Ea over RT will also decrease. So when e power Ea over RT decreases, what happens to 1 by e power Ea over RT? This increases, right? So this term, or I can say e power minus Ea over RT, increases with increase in temperature. So when this term increases, if you consider A as a constant, K will also increase, right? So if K increases, that means rate of reaction is increasing. So with increase in temperature, rate of the reaction increases. So this is from the equation we see, but here we can explain the same thing using this energy profile diagram. Let us see how. So if I increase the temperature, what will happen? I'm increasing the temperature. That means I'm giving energy to the reactants. So the reactants will have higher energy. So at higher temperature, the reactants will have higher energy. Suppose they have, say, some 50 joules. Okay. Now they need to acquire, not 50, say 60. Okay. Now they need to acquire only 40 joules of energy to cross this energy barrier. That means the activation energy here will only be 40 joules. So by increasing the temperature, we are decreasing the activation energy for the reactants. Okay. So we are not decreasing this, but we are increasing the energy of reactants. So activation energy is getting decreased. So since the activation energy decreases, it is easy for the molecules to acquire this 40 joules and they can be easily converted into products. So this is why on increase of temperature, rate of reaction increases. Now we'll see how activation energy affects the rate of reaction. Okay, suppose if activation energy increases, what will happen to this term Ea over RT? Activation energy is in the numerator, so this term will increase, right? So what will happen to this e power Ea over RT? This term will also increase, right? Since this exponent is increasing, e power Ea over RT will also increase. So if e power Ea over RT increases, then what happens to 1 by e power Ea over RT? That decreases, right? That means e power minus Ea over RT decreases. So we see that with increase in activation energy, this term is decreasing, and if we consider A as a constant, with decrease in this term, rate constant will also decrease. That is, with increase in activation energy, the rate of the reaction decreases. Okay. So it can be easily explained from this energy profile diagram. So if we increase this activation energy, what will happen? If I make this activation energy as 120 joules. Okay, if I make this activation energy say as some 120 joules, what will happen? Earlier the molecules needed only 60 joules of energy. So I am considering the first condition. They had 40 joules. They needed only 60 joules of energy to cross this energy barrier. Now they need 60 plus 20, that is 80 joules of energy to cross this activation energy barrier, okay, or threshold energy barrier. So that means with increase in activation energy, more energy is required for the reactant molecules to give products. So that will be even harder. So the rate of reaction decreases. So with increase in activation energy, rate of the reaction decreases. Now what happens when I decrease the activation energy? Suppose if I decrease it to some 80 joules. Okay. The molecules already have 40 joules. In the normal condition, they needed to have 60 joules, but since I have decreased the activation energy, now they need only additional 40 joules to cross the threshold energy barrier. So they need less amount of energy. So more number of reactant molecules will be converted into product in that case. Okay. So with decrease in activation energy, the reaction becomes faster and rate of reaction increases. So with decrease in activation energy, rate increases. Now you can ask me one question, that how can we increase or decrease the threshold energy or activation energy for any reaction? So that can be done with the help of catalysts. So catalysts are what do? They alter the mechanism of the reaction and thereby altering the activation energy. So they make the reaction to happen in some other pathway so that their activation energy decreases. Okay. So this way, by using a positive catalyst specially, so this positive catalyst will lead to decrease in activation energy. Therefore, with addition of catalyst, rate of reaction increases. So this is in the presence of catalyst. Okay. So that is positive catalyst. Then how can one increase the activation energy? So there are special catalysts called negative catalysts or poison catalysts. Okay. So those are called poison catalysts. So these catalysts will alter the mechanism in such a way that the activation energy increases. So these catalysts are used to slow down any reaction. So in this case, negative or poison catalyst is used. So poison catalyst. So here we see how activation energy and temperature affects the rate of reaction. Now we will see different forms of the Arrhenius equation. So one form we know, that is K is equal to A e power minus EA over RT. Now this can also be written in the form of logarithm. Okay. So if I take ln on both sides, I'll get ln of K. This is the natural logarithm. Okay. Ln of K, ln A plus ln e power minus EA over RT. So if I consider it as A and consider this as B, so ln of AB will be equal to ln A plus ln B. Okay, this is the basic formula in mathematics. So ln K is equal to ln A plus ln e power minus EA over RT. So the base of this ln will be E, right? This is natural logarithm. For natural logarithms, the base is E. And for the other logarithms, log form, you have the base as 10. Okay. So since the base is E here, ln E, base E becomes 1. So this becomes 1. So you can take, okay, ln A power n will become n ln A. So this is also one formula. I hope you all know this basics. Okay. So this is ln A power n is n ln A. Okay. So I can write this as ln A minus EA over RT ln E. So ln E. So the base of ln is E. So ln E base E will be equal to 1. So this term becomes 1. Now what you have is ln A minus EA over RT. So this is one form where ln of rate constant is equal to ln of A minus EA over RT. So let us see how it can be explained with the help of a graph. So if you consider this as y coordinate, and this is since we consider A as a constant here, so ln A will become constant C minus, so if you consider 1 by t as x coordinate, then m, this is n. So this equation is of the form y is equal to C minus mx, which is a straight line equation with negative slope. So how does the graph look? The graph between ln k and 1 by t. So it looks something like this. So here the y-intercept is C, that is ln A. So this will be ln A, and what will be the slope? I can write this as EA over R into 1 by T, right? So this is M, this is X. So X is 1 over T. What is the slope here? Minus EA over R. So from the slope, from the graph of ln K versus 1 by T, you can find the activation energy by looking at the slope. So if you are given the slope and if you are asked to find the activation energy for a particular reaction, for this Arrhenius equation, what do? Activation energy is equal to S into R. Okay. So from the slope of ln K versus 1 by T, you will get the activation energy for any reaction. Okay, there is one more form which is very important and it is called integral form. So this is one form. This is the other form. Now what will be the graphical form for this equation? Suppose if I draw K versus T. So what happens if T increases? Rate of reaction will increase, right? And this is an exponential equation. This is an exponential term. So the graph will be exponential. And if T increases, this term will increase. So the graph will be something like this. Exponentially increasing curve. Okay. The graph between K and T will look something like this. Now the third form is the integral form. I think I'll do it here. So now we have the second form, that is ln K is equal to ln A minus EA over RT. So what I will do, I'll take the differential of this form. So d by dt of ln K is equal to d by dt of ln A minus d by dt of EA over RT. Okay. So now if I differentiate this complete equation, let us see what will we get. So this will be d ln K over dt, right? So here we consider A as constant. Actually A is not a constant. Later they came to know that A is not a constant. But when this equation was given, A was considered to be a constant. So when A is considered to be a constant, differential of constant is 0. So now EA over R is a constant, so I can take it out and I can take differential of 1 over T. So T can be written as 1 by T can be written as T over minus 1. So what will be its differential? Minus 1 into T power minus 1 minus 1. That is minus 1 by T square. We know that x power n is n into x power n minus 1. So d by dx of x power n is n into x power n minus 1. So I have used the same formula here. Okay. So I can replace this d by dt as, what did we get? Minus 1 by t square, right? So this will be minus 1 by t square. So d ln K over dt is minus into minus becomes plus EA by RT square. Now I integrate this equation. So this is the differential form. So we'll get the integral form by integrating this equation. So we'll consider two limits. That is, suppose K1 is the rate constant at temperature T1 and K2 is the rate constant at temperature T2. So the limits will be K1 and K2 for rate constant and T1 and T2 for temperature. Okay. So this will be, okay, for differential you need to, for integration you need to write dt here. So differential and this integral will get cancelled. What you have is ln K now. So this is between rate constant limits K1 and K2. So this is equal to, so EA over R is a constant, dt is missing here, Okay, 1 by t square into dt. I need to integrate it between the limits t1 and t2. So what is the integration of 1 by t square? We know that integration of x power n is equal to integral x power n dx is equal to x power n plus 1 by n plus 1. So we are going to use this formula to get the integral of 1 by t square. So we know that this is 1 by t power minus 2. Sorry, t power minus 2. So what we have here? So the integral of t power minus 2 will be t power minus 2 plus 1 by minus 2 plus 1. So this will be t power minus 1, and in the denominator you have minus 1. So this will be minus 1 over t, right? So this is minus 1 by t. So this will be equal to EA over R, and the integral was minus 1 by t between the limits t1 and t2. Now I'll substitute the limits, okay? So upper limit minus lower limit, that will be ln k2 minus ln k1. So here we have EA over R minus 1 by t2 minus 1 by t1, okay? So the way we do is we first substitute the upper limit and then minus lower limit, okay? So this is how we do. We know that ln A minus ln B is equal to ln A by B. So ln K2 minus ln K1 will be ln K2 by K1, okay? And here this becomes minus of minus will become plus, and you have minus 1 by t2 plus 1 by t1, or you can write it as 1 by t1 minus 1 by t2. So this becomes, if I take the LCM, this becomes EA over R t2 minus t1 by t1 t2, okay? So ln k2 by k1 is this much. So this is the integral form of Arrhenius equation. So when you are given two rate constants and only one temperature, or if you are given two temperatures T1 and T2, and you are given the rate constant at T1, and if you are asked to find the rate constant at T2, then this equation will be very helpful. Suppose if you are given both K2, K1, T1 and T2, they can ask you to find the activation energy, okay? So this is how you use this equation in the problems. So this equation is also very important to solve the problems. So I am going to, okay, I think you have noted this down. So the third form is the integral form, and which is very important to solve problems, okay? So the third form you have is ln k2 by k1 is equal to EA over R t2 minus t1 by t1 t2. So if you want to write it in the form of log, what do? You know that ln is equal to 2.303 into log, right? So this is log to the base 10. ln is to the base e, okay? So I can write this as 2.303 log k2 by k1 EA by R T2 minus T1 by T1 T2, or you can write it as log K2 by K1. So I'll bring it on right side. What does it become? EA by 2.303 R into T2 minus T1 by T1 T2. So these two forms are the same, but this is expressed in the form of ln, which is to the base e, and this is expressed in the form of log, which is to the base 10. So you just have to divide on the right side by 2.303 to get this equation, okay? So I hope all the concepts have been cleared in this video, and if you have any doubt, you can ask me in the comment section. And there is one more important question. So if you know the answer to the question, please do answer in the comment section. So I have told you about A. that is pre-exponential factor. So here we see that this is an exponential term, right? And this factor comes before this exponential term. Therefore, this is called pre-exponential factor. Now my question is, what are the units of A? So what are the units of pre-exponential factor? So do let me know in the comment section. Thank you so much for watching the video, and in the next video we will solve problems on this topic. Thank you. Bye bye.